Okay, welcome. Let's just go to the next slide. So today we're going to talk about featurization at Two Sigma using Ibis, Substrate, and Apache Arrow. A rather long agenda, but I'll start by introducing myself, the story of how I met Wes and what we've been working on over the last 6 or 7 years, the challenges that we see at Two Sigma moving forward, and then I'll turn it over to Wes to introduce himself and the work he's been doing specifically with Arrow, Ibis, Substrate, and looking forward to what we're planning over the next couple of years. So with that, let's move to the next slide. So I'm Dave Palaitis. I'm a managing director at Two Sigam Investments, where I'm responsible for building out the research and production, data analytics, and machine learning platforms for our investment management business. Before I really go any further, I need to note that nothing I present here can or should be considered investment advice. This is a purely technical and abstract talk, probably too abstract, as you'll see soon, but that's just the nature of our business. So don't listen to anything I say about investment advice. Next slide. So I've worked at Two Sigma since 2011, and when I joined, our research and production modeling platform was all built on top of the Java virtual machine. Modelers wrote models in Java, and they did all of their research in Groovy. After a few years of getting experience building out that modeling environment and scaling our compute capacity across the JVM, I initiated the transition of our platform to Python. I really wanted to allow modelers to use NumPy and pandas, which had become hugely popular in the quant software development community at the time, much due to Wes's work in the community when he was at AQR. My first step in making that transition was really to hire the best possible people I could to work with me on that, and I was lucky enough to hire Jeff Reback, who's currently the principal maintainer of pandas, and then hired Wes in 2016 to work with us together. When Wes joined, Arrow was just getting started but we really adopted Arrow internally and worked to push that forward as a standard within Two Sigma. Wes and I really shared a vision for the future of data science at that time, and both agreed that we needed to be able to exchange and manipulate data across system boundaries, and that was the key to the future. So we introduced Arrow to Two Sigma and used it as the in-memory format for interoperability across our systems. But we also worked with Wes in the open source community, and we had a really big win in 2017, where we added pandas user-defined function supports for Spark using Apache Arrow to move across the language boundaries. That was a huge win for Two Sigma, as it allows us to have our modelers use pandas, but also a big win for Arrow and brought it really into the mainstream. Wes left Two Sigma in 2018, but we continued to work with him since then, specifically on using Ibis, a transpiler that allows us to write models and do research in Python, but then execute that on multiple backends, including our internal trading systems. And more recently now moving towards streaming analytics with the open source projects Arrow and Substrate that will allow us to support petabyte scale data analytics. Next slide. So before I move to Wes, I want to step up maybe 100,000 feet and try to present the problem we are solving with all of these technologies. So featurization is the process of transforming raw data sets, for example, a Twitter feed or web scrape data, in our case, market data, into sets of normalized time series that we call features. These features are then used as inputs into Two Sigma's machine learning models. Next slide. So I realized writing this talk, in my 10 years at Two Sigma, I've basically been building out technology platforms to solve this equation. In grade school, we learned this equation as y equals mx plus b. It's the equation for a line, and we learned how to solve it using a closed form. If we go to a computer science program and do linear algebra, we learn the matrixed version of this, where x is a matrix and y is a matrix, and we want to solve for the parameters that solve that. And finally, in machine learning, we have the same equation, but we're now trying to find this function f that minimizes the error, epsilon, to learn the values of theta, which are our modeling parameters. This is pretty abstract, but basically in the investment management business, if you can minimize this epsilon, you can effectively predict the future. Or if you're building ChatGPT, it's sort of the same thing. If you can find this function, you can predict the next sequence of tokens that the user, would be satisfied with when receiving this prompt. Next slide. So the X in this the equation is really important. In any TensorFlow or PyTorch tutorial, it's common to see the features used in a model referred to as the X's. And internally, we tend to call these the X's. Essentially, all of the work that Wes and I have done over the last 8 years is in support of data scientists and modelers need to convert raw data that's incoming into these X's. Next slide. So a machine learning algorithm can't use raw data in its input form. And raw data needs to be normalized into something that tends to look like a multidimensional matrix or a matrix of tensors. And this is the form that a feature takes. And all of the work of featurization is taking raw data and transforming it into this form. But the technology and the stack and languages that we use to do this is incredibly complex and really what we've been working with on over the last many years. Next slide. It's typical to represent featurization as a series of steps or nodes in a directed acyclic graph. So you have some raw data, maybe 1 or 2 or 100 sources coming in. You do some operations on that data. You join those data sources together in time, do some aggregations or group by operations on them, and finally end up with a feature. This is the stuff of Arrow, Ibis, and now Substrait and Acero that we're making possible for our modelers to do across language boundaries and across distributed systems like Spark, Dask, and Ray. So next slide. I've learned over the years that this is incredibly challenging, and it's challenging, I think, for 3 reasons. And the work we're doing with Voltron is going to address some of these. So first, how do we represent these features in memory and on disk across distributed compute clusters and multiple feature engines? Second, we need to support multiple feature engineering teams that are doing this work. And it's not possible to really have a single standard for how these teams do this work. They need to have optionality, but then they also need to have interoperability. And that's a really big challenge for us, as we don't want to limit the choices our data analysts and modelers can make, but we still want to be able to have interoperable systems. And finally, the scale is just growing so quickly. When I started in 2011, a large feature set would be maybe 300 gigs on the largest size. 2020, we started to get into terabyte scale. And now looking ahead, as we look to the future, we're really hitting like even petabyte scale for the number of features that may be input into machine learning algorithms. So our ability to scale even Dask, Ray, or Spark, or those clusters is becoming limited. And we're really looking at streaming models for analytics, along with Wes, out to the future. So with that, I think I'll introduce Wes, and he'll talk about the collaboration that we have together, and the work specifically he's doing on Voltron data and how it applies to what we're doing here at Two Sigma. So thanks.
Thank you, David. It's been it's always amazing to to contemplate the the years going by. I think David and I first connected in 2016, shortly after the Apache Arrow project was created, and that's already been 7 years. But it takes a long time to build out these these ambitious open source technology visions. But we have really come a long way over the recent years, and certainly myself and my work in Apache Arrow, I owe a great deal to Two Sigma and their being an early true believer in the projects that I've been working on in the last decade. So many of you know me as the creator of the Python Pandas project, which will have its 15-year anniversary this spring, which is dating me a little bit. I did start out in the quant finance world, is where I got interested in Python and data analytics, and started building what became the Pandas project. But I haven't been a full-time maintainer or developer of Pandas over the last 10 years. So, as David mentioned, I handed off the Pandas project to the open source community in 2013, and Jeff Reback and the other Pandas core developers have taken over and grown the community around Pandas in the intervening years, turning it into the juggernaut of an open source project and community with over 2,000 unique contributors and a thriving ecosystem of packages and development happening around the Pandas project. But the experience of working on Pandas led me to a number of significant infrastructural problems in data science and data analytics that, in my view, were impeding progress to, firstly to make Python a more relevant language for data science, but also to help scale and coalesce efforts to build more composable, scalable, and high performance data systems. So two of those projects that I became very involved with, after ceasing full-time work on Pandas. The first was the Apache Arrow project, which I'm going to turn to next. Another project that I was working on at the same time was Ibis, which I will also talk about. I also will speak a bit about our work at Voltron Data and how we are working to accelerate the growth of these new open source ecosystems. So Apache Arrow has been around as an open source project for 7 years now. The project has its seven-year anniversary in February. And for me, when I started becoming interested in this project, I was experiencing the pain of building data connectors between pandas and different big data analytics systems and storage systems. And around the same time, I discovered that there were many developers who were frustrated about this same problem of data interoperability across computing systems and storage systems. And so we got together and said, what if we designed a language-independent, universal, column-oriented data format, essentially a portable data frame, which could be used as a unifying interchange layer between all of these different systems, which could help build more efficient, more composable, polyglot data processing systems. And so we needed the memory format to not just be sufficient for interoperability, but we also, because we wanted to reduce serialization and the copy and conversion penalty that you traditionally see between systems, the memory format needed to be designed for high performance execution directly on the Arrow memory. And so over the years, we've been focused on these four key areas. So firstly, sharing data, sharing memory very efficiently between processes and systems, supporting technology to enable the creation of very fast distributed systems that are Arrow native. We obviously need to integrate with all of the storage, file formats, and database systems where data is stored so that we can get data out of systems faster and into the applications where it needs to be processed. And in more recent times, we've been increasingly focused on building accelerated processing engines for working with larger than memory data sets and executing complex analytical queries on the Arrow data format. So the things that are leading developers and system developers to use Arrow for their systems, certainly for the end users, systems that are built on Arrow are faster and more efficient. You can plug together systems that use Arrow very easily. You don't have to think about writing data connectors, maintaining a custom bridge to serialize data between one format and another. This leads to a better developer experience. Systems run faster and more responsive. Because Arrow is polyglot, this simplifies interchange at language boundaries. And so we can see systems that are built in Java, Go, Rust, C++, JavaScript, and they can all unify on the Arrow format and move data between their environments much more easily. Developers love Arrow because they can focus just on a single memory format for working with tabular data. And this also enables computational engines to be repurposed and reutilized within different languages and within different systems much more easily. So this means less code to maintain and more developer time can be focused on common analytical processing components, so we can focus on optimizing fewer things and then reuse them in many places. Another aspect in modern times, which is important with Arrow, is being able to use modern silicon. So in particular, using GPUs to accelerate data processing. And with the innovation that's happening in the semiconductor industry, it is easier and easier to develop custom hardware for computing. And we believe in the future we will increasingly see custom chips which are optimized for analytical processing. And we are by using Arrow, we simplify the problem for the hardware developers, where they can specialize their hardware capabilities toward processing Arrow. It's been really exciting to see the uptake in the open source community, in database systems, distributed processing engines. A lot of the major tech companies are using Arrow for different layers of their stack to accelerate connectivity to the data science ecosystem, to improve processing efficiency, and to make their systems faster, simpler, and more efficient. The project has seen this major traction over the recent years. We recently, in the last year, saw hockey stick level growth in the adoption of the project as a dependency in downstream open source projects and systems. And we believe that this trend will continue as Arrow continues to become the de facto standard and an essential part of building modern data processing systems. In the last few years, after we hardened some of the core protocols and specifications for Arrow, our effort has shifted to working on building Arrow native data processing engines. And so the idea here is that it's great to use Arrow to improve interoperability and reduce serialization costs in connecting systems, connecting programming languages, but to also be able to execute SQL and complex analytical queries in a highly optimized way means that we can create these fully Arrow native systems that are an order of magnitude faster or more than the last generation of data systems. We can also, by virtue of standardizing on an invariant memory format, we can utilize hardware acceleration much more easily, taking advantage of things like Rapids, which is NVIDIA's GPU acceleration library for analytics with Apache Arrow. And so some of the projects that you may be familiar with, like Rapids, DuckDB, a new embeddable database engine, Data Fusion, Polars, these projects are being built targeting Arrow as a primary data format, and that's very, very exciting. So shifting gears a little bit, around the time that I started getting involved in the Arrow project, while I was at Cloudera, I started a project called Ibis, which was solving a different side of the coin of building more modular and composable data systems. And so if you think about the pandas library, many of you on the call I'm sure use pandas, but pandas has an API for describing analytical operations that is very specific to the implementation of pandas, the way that data is represented in pandas, and the way that the computations are executed. And so around the time that Ibis started, there wasn't really a robust solution for expressing complex analytical data frame operations as at the complexity of what you can do with pandas, but where you can create a query expression that can be rewritten or transpiled into SQL so that you can more portably use other execution engines. And so we started this project initially with the idea of building a more Pythonic data frame-like experience for authoring, writing complex analytical query expressions, and then building a number of backends to be able to transpile those queries, those expressions into SQL, and to be able to target other non-SQL based execution engines. And what was interesting, one of the things that we wanted to do with Ibis was to enable use of systems beyond SQL and to be able to make it extensible to specialize to different types of analytical systems, different types of storage engines, so that we can have a common medium for rewriting queries, optimizing queries, and making analysis more portable across environments. So using Ibis, a developer can both write very complex expressions that they can create very complex analytics much more productively than they can with SQL, while also having this really robust developer experience that does query validation, type checking, a lot of analysis, and it catches mistakes that you make while you're writing complex expressions, while enabling to reuse your analytical expressions much more easily than you could with SQL. So I'm sure many of you have had the experience of copy and pasting SQL and like rewriting a little bit, or like copy and pasting a fragment of SQL into to a different application. Ibis makes all of this go away while producing a much better developer experience. So it's been an exciting project to build out. And Two Sigma has been able to take advantage of Ibis to bridge, to create a unified developer experience across a variety of different types of computational systems. So the last component, which helps bring all this, tie the room together, so to speak, is Substrate, which is a developer-centric project, but it provides an intermediate representation for describing complex analytical operations in a language-independent and back-end independent way. So so what Substrate enables us to do is to decouple front-end user interfaces like Ibis from back-end execution engines like Arrow, Data Fusion, Acero, Spark, and SQL engines like BigQuery or Snowflake or DuckDB. And so we've worked to generalize what is possible to express in Substrate so that we could target all of these different execution engines. And so in the Python and R environments, we've been working to build Substrate interfaces to Ibis, as well as Substrate interfaces to dplyr, to enable Python and R users to develop to create Substrate expressions through a familiar syntax. And so what's exciting now is that rather than having, a proliferation of pairwise interfaces between APIs and backends to maintain, we can start to think about using Substrate as the standard interface to backend execution engines. And so we focus on building, a Substrate interface to each different execution engine. And then on the front end, all we need to think about is how to generate Substrate. And so this makes the development problem for us, the open source maintainers, a great deal easier to maintain. And we can also start to think about building systems that are Substrate centric around query planning, query optimization, so that I think that we will see a rich ecosystem of open source software developed that is focused on query optimization and infrastructural problems within Substrate. So we've been working for many years with Two Sigma on these problems. So my company, Voltron Data, we're a venture-backed startup building open source software and systems around these problems. Working to accelerate the growth of the Apache Arrow ecosystem, making it easier to build, composable, modular, reusable, accelerated data systems powered by these projects, Arrow, Substrate, Ibis, and so on. So I believe that we'll continue to see accelerating growth and adoption in these projects, and I'm excited to see what the future holds. So thank you for your attention, and I believe we have a few minutes for some Q&A.
Yeah, thanks, Wes. I also want to say that while Wes and I both work for companies, we could never build this software without big contributions from the open source community, whether it's Arrow or Pandas, Ibis, Substrate. I encourage everyone to get involved with those projects. There are entry-level issues for all of those projects, and there are many ways to get involved. And by learning about this stack, I think we just create more value for the world as we move to a new generation of data science and data scientists. So thanks again.
Q&A session. Can Apache Arrow be used for image data also?
Yes, it can. So there's actually a project called Lance. It's an Arrow-based data format. It's like a file format it's basically Arrow plus some extensions for dealing with image data sets for machine learning. And so they've built some extensions for DuckDB that enable you to do certain image processing featurization workloads against image data sets. So you imagine if you had a collection of images, you can represent those. You can embed images in an Arrow column, like a binary data type, and then you can you could write user-defined functions which could be run within your target database engine of choice to execute image functions on the data set. So maybe not an obvious fit, given that it's Arrow is very oriented towards structured data, tabular data, data frames, but it is possible, and there are developers that have done that successfully.
Not a question, but a comment. You are doing great work, Wes. Without pandas, I would not be able to analyze data in Python.
Well, thank you. Certainly thank the developer community for making the project as stable and featureful and well documented as it is today. It's been really gratifying for me to see the growth of the community and to help support it over the years. I just published the 3rd edition of my book, Python for data analysis, and so it's been now 10 years since the first edition came out, and it's interesting to see with that perspective on how the ecosystem has developed. I think a decade ago we had the aspiration of making Python a popular language for data science, but at the time it wasn't at all clear that was going to be the case. And so for me, now that Python is a mainstream programming language, I think with the work that David and I have been doing together has been enabling Python to be used at scale in building these large and performance critical production systems. And so we need to enable Python to be able to drive these mission critical production systems and to be able to achieve best-in-class performance and efficiency, because in this day and age, computing computer time equals money, and so we want to be able to build systems in Python that where we're not giving up performance, or we're not less efficient because we choose to build them in Python, and that's really been motivating this kind of open source infrastructure work, which has enabled us to make systems that are a lot faster and more scalable.
Towards the year end in December, I had to do Jeff Breback's year end review. He wrote a self review, and one of his line items was, did 1,500 pull requests for the Pandas project. which is pretty heroic. It's the amount of activity in that project is amazing, and the few people that keep that running and the work that they do every day is phenomenal. Yeah.
All right, looks like we have another question. What is next on the Arrow roadmap?
Well, there's a bunch of things. Given that it's a large community, I think integration, deeper integration with Substrate, enhancing the features of these execution engines, the Arrow engine in C++, data fusion in Rust. Building. We have a couple of projects for enhanced database integration, ADBC, and Flight SQL. So we're working with database vendors, open source database projects to make it easier to run SQL queries and get Arrow data out, and vice versa, so that we can have more Arrow native interfaces to database systems. So I think the roadmap is really focused on improving connectivity, enhancing data access performance, and improving these open source query engines and making them easier to invoke in different applications through Substrate.
Cool. Yeah. Thanks for having us. Take care.
All right.